Important application of the inverse function theorem is that from well-known functions we can derive others. Remember how we defined the logarithm in the Math 1 course? Well, the natural logarithm was defined as the integral from 1 to x, where the integrand was given by 1 over t. Right? So, and this function was defined from 0 to infinity. Okay? Well, e to the power x is the inverse of the natural logarithm, but it was introduced differently. We just look at the class of functions of the type a to the power x, and we defined e to the power x as the unique one in this family for which the derivative at 0 was equal to 1. Well, it's not at all clear that such a number e exists. So here we will derive a function e to the power x as the inverse of the natural logarithm in a different way. Okay, first what we're going to do is show that the log of the natural logarithm of the interval 0 infinity is in fact the image of the 0 infinity interval is exactly r. Well, the way we're going to do this is we're going to look at the two sequences. So a proof is easy. So we're going to look at the logarithm of 2 to the power n, which is the same as n times the logarithm of 2. And the logarithm of 2 is a positive number, since we have the integral from 1 to 2 over a positive function. So the area under the graph 1 over t from 1 to 2 is a positive thing. So the logarithm of 2 is a positive thing. So when we now increase n to infinity, then the logarithm of 2 to the power n also goes to infinity. On the other end, if we have the logarithm of 2 to the power minus n, and this is the same as we know as a logarithm of half to the power n, which is the same as n times the logarithm of a half. Well, the logarithm of a half is the integral from 1 to a half over a positive function. Yeah, but we should change the integration order, which creates a minus, so the logarithm of a half is a negative number. Right, so this one is a negative number, n is a natural number positive, so this one goes to minus infinity if we let n go to infinity. Right, so in particular, if x is larger than 2 to the power n, the ln of x is larger than n to the logarithm of 2. And if x is smaller than 2 to the power minus n, the logarithm of x is smaller than n of the logarithm of a half. Right? This basically shows that the logarithm of the image of the set 0 infinity is just r. By using the intermediate value theorem, since the logarithm of x defined as a primitive over 1 over t is a differentiable function and is therefore also continuous. So it attains all values between infinity and minus infinity. That's the logic here. Right. So also we see that the derivative of the ln of x is 1 over x, right? As it is a primitive of the function 1 over t dt. It's a primitive of the function 1 over x, right? So we see that the ln of x is a strictly increasing function, and it maps the 0 infinity onto r. So it has an inverse, right? So the inverse is now the exponential function, which is defined as the inverse of the natural logarithm. We know that it exists. Right. Also, the inverse function theorem tells us something more, right? So if we focus on a fixed point, like we did in the inverse function theorem, we know that at each point the logarithm the derivative of the logarithm in some arbitrary point a is 1 over a, right? And since a belongs to the domain 0, infinity, this derivative is always larger than 0, right? The logarithm is a strictly increasing function. So we know by applying the reciprocal formula for the derivative of the inverses, we get that the derivative of the exponential function defined as the inverse of the natural logarithm is just 1 over the derivative of the natural logarithm evaluated in the exponential function evaluated in x, right? Okay, but there's an easy formula for this derivative of the natural logarithm. It's just 1 over the argument, right? So it's 1 over the exponential function in x, so which yields the exponential function in x. Yeah, that's the basic fundamental property that we now get as a result without assuming that there's a value e. Okay, we have further properties of this function, this exponential function, we can show. For instance, we have the property that the exponential function differentiated in 0 is the exponential function in 0, which equals 1, right? And why is that? Well, the exponential function evaluated in 0 is 1, since its inverse, the logarithm of 1, equals 0. Right? So this was an essential property that we assumed in Math 1, in the Math 1 calculus course. Okay, there's also another property, so that if we exponentiate x plus y, that is the same as the exponential of x times the exponential function evaluated in y. Well, how can we see this? Well, just write x equal to the log of u, and y is the log of w. Since x and y are members from x and y are in member of the real numbers, such u and w must exist, and these values are unique. Okay, so the exponential function evaluated in x therefore equals u, and the exponential function evaluated in y therefore as the inverse of the log equals w, right? So if we now write the exponential function evaluated in x plus y, then what do we get? The exponential function in the log of w, log of u plus the log of w, right? Okay, but now we use the known formula for logarithms. If we take the sum of two logarithms, we get the log of the products. Well, at least when u and w are positive, but in this case they are, by assumption. So here we get the exponential function evaluated in the natural logarithm of u times w, which means the exponential function and the logarithm being each other's inverses, that these cancel. This is no more than the identity. So when this is no more than the identity, what remains is u times w. And u times w, we chose u being the exponential function evaluated in x, and w is the exponential function evaluated in y. So we get x times the y.